Hi guys, so a few moments ago I just finished going through torsional divergence, and we sort of had the idea that there's all these things that we could do on an aircraft to increase the torsional divergence speed. So we can fly high, we can have a big stiff wing, or we can have a small elastic margin, or ideally a zero or negative elastic margin, in which case our aircraft can never succumb to torsional divergence. So I've asked this question here: why do most aircraft have aft swept wings? Now, the answer is probably obvious now. It's to reduce the likelihood of torsional divergence. Now, we're going to go through this today. We're going to look at the mechanism via which sweep helps us, or specifically aft sweep helps us to avoid torsional divergence, and hopefully just give you some interesting ideas about effectively why aft sweep is actually not that good aerodynamically. So let's talk about it. So we're often taught that, let's do a little bit of a refresher on what sweep is, because I know I've got mechanical engineers in this class as well, and I've got some aeros who probably need a bit of a refresher. So I'm only ever good at drawing aircraft this way round, unfortunately. But let's draw my aircraft. It would be easier if I could draw it the other way around, because I could draw the lateral axis as being the y-axis. But this, imagine if I have an aircraft that looks like this, I could draw a line down the semi-chord line of my wing. And I could also draw on here, I could draw aircraft body axes. And you'll learn these in aircraft flight mechanics. Hopefully you can see these in the notes, but we have X, Y, and Z, which means my aircraft lateral axis and the semi-chord line are often not coincident on my aircraft. And if they're not, that means we have a degree of sweep. So this angle here between the semi-chord, or between however we're defining it, we can define it on the quarter chord, the semi-chord, or maybe sometimes the leading edge. But this angle here is given the symbol lambda, and this is wing sweep. And it's defined: if it's positive, it is aft, and if it's negative, it's forward. So what we see on most aircraft you'll ever see flying, there are some notable exceptions, but most aircraft you'll ever see will have this aft sweep to their wings. Now, let's go over why that's present on aircraft. And we'll talk about some of the things you might have been taught before. And what I'm saying is none of what you've been taught before is wrong per se, but often the idea of why we have wing sweep is somewhat, it's explained for sometimes the wrong reasons, we'll say. So we are often taught that the Mach number is reduced in the section comprising a wing, something like m prime is equal to m cosine gamma. Okay, so we're often taught this is true, and it can be true, and it can help us certainly if we've got, say, a fighter aircraft that's specifically going in the transonic regime. But let's think about the following. So most airliners have sweep. Most airliners only really go 0.7 to 0.8 Mach. Okay, and most of these airliners have also got supercritical sections, so it doesn't really help us on airliners. Also, light aircraft often are present with a degree of wing sweep as well. And in fact, you'll see some gliders that have aft wing sweep. And also, if this was the only reason why we had aft wing sweep, then why wouldn't we have forward sweep? Okay, forward sweep would be the same thing because cosine of minus theta is the same as cosine of minus lambda is the same as sine of minus lambda. So that wouldn't affect this equation here, and we'd have the exact same thing. And in fact, forward sweep is often preferable aerodynamically. Okay, so it's often preferable for high angle of attack and maneuverability. I can only spell this word the British way. I had to learn a long way to learn to spell that. But forward sweep is often preferable aerodynamically for both high angle of attack and maneuverability. So let's look at what happens if we have both a forward swept planform and an aft swept planform at some high angle of attack where we have an increase in lift on the wings. Let's look at the aft sweep first. So if we have a set of wings with aft sweep, so we've got our wing here and we've got our two ailerons present on the wing. Then if we have an increase in angle of attack suddenly on this wing, then we're going to have shed some circulation into the wake. Okay, so you can probably remember this from, I think you've gone through this in 312 aerodynamics of aerospace vehicles. In the circulatory theory of lift, with the wing, the pressure difference is sustained by a bound vortex, and if we increase the strength of that vortex, we've got to shed an equal and opposite amount into the wake. Now, when we've got aft sweep, these root sections cause this circulation to be shed into the wake, which causes an upwash at sections outboard of there. And in fact, I should have written up here, this is my U. So sections shed circulation due to any change in angle of attack, and that's going to cause an upwash at all sections outboard. Okay, so I should draw this in green. So we see this upwash at the tips, which causes an increase in angle of attack at the tips, which means if we have this sudden perturbation of angle of attack, it's going to cause circulation to be shed here, which causes a further increase in angle of attack at the tips, and that's going to cause the lift distribution to have this peak at the tips. Let's erase that part here that I tried to draw. I can't get rid of that for some reason. There we go. So we see this peak at the so this is my lift distribution. So because of this upwash at the tips, because of shed circulation on any section inboard of the tips, we see this increase in the lift distribution, increase in alpha, and then what this is going to cause, it means the tips are going to stall first, because they are going to, when we have any velocity perturbation, any alpha perturbation, you're more likely to see a tip stall. Again, if we have a tip stall, then it means that we lose control effectiveness. It means that the flow over the ailerons is subject to, we've got separated flow, so we lose the ability to lose the controls. Okay, so we've got that one there. Let's just look at the same phenomena occurring on a forward swept wing. We've got U here. Now if we have the same thing, we have a perturbation in alpha, and we're going to shed the same circulation from the trailing edge. Now this is being defined in the opposite sense to the bound vortex. Again, this should just be a revision for you guys, or a recap of what you covered in 312. Now what this means that actually from the root sections we have a downwash at the tips. And again, so we can't affect this upwash because now this downwash here. So when we have any perturbation in angle of attack and a perturbation in the strength of the bound vortex, this shed circulation here instead causes a downwash. And effectively we just see this as being a downwash at the tips, which means that our lift distribution is much closer to lift. Looks like all of my equipment is failing just as I'm finishing being a professor, so this is probably good. There we go. Okay, so we then see this downwash at the tips, and we have a lift distribution that's much closer to being elliptical. But effectively we see this nice lift distribution without this sort of upwash that's occurring close to the tips. And what that means is that the high alpha, or the highest angle of attack, I don't know, I've drawn my control surface there, the highest angle of attack is actually going to be at the root. So what we see here is that we have a root stall. Let's draw this in the same colours as I did before. So we have a root stall that occurs with forward sweep, unlike with aft sweep where we have a tip stall. So if we have a root stall, what that means is that the ailerons are still in attached flow. So we have nice controlled, nice controllability post stall. And again, if we have this stall that's occurring here, in general this won't be convected down the wing because we've got the wings are forward swept. If by contrast, if we were to have a root stall on the forward swept wing, this would have a tendency to propagate downstream and again down along the wing. So even if we could have a root stall here, we'd still have a tendency to see this go onto the ailerons. So this fact means that for controllability and maneuverability, this is often better, but also when we've got a lift distribution that looks like this, we're going to have a tighter tip vortex. So we're going to have a stronger tight tip vortex. Whereas by contrast on this distribution here, we'll have a weaker tip vortex. So just for performance side of things as well, in general, for the same net circulation distribution, we would have a weaker tip vortex, and thereby we'd have lower induced drag. So again, this stuff, I'm not expecting you guys to be able to remember and regurgitate all of this stuff, but I want you to understand that if sweep was just about improving aerodynamic performance and for the idea of having this reduction in critical Mach number, and it was purely an aerodynamic effect, then forward sweep would be better because it's often increases controllability and maneuverability post stall, and there's also this performance benefit. So we'll say that forward sweep we'll say that forward sweep is better for maneuverability and for performance. So there must be something else that's going on an aircraft, which is why we see all airliners in general have this aft sweep. I realise I've got a nice straight wing on my aircraft here, but most airliners that you'll see will have this element of aft sweep to their wings. Now, what is it? You've probably guessed, and in fact I've already told you, it's to increase divergence speed. So let's find out why. So the reason for aft sweep to be employed on aircraft, to be employed in favour of forward sweep and on slow aircraft is because it increases divergence speed. So let's think about why. And we're going to remember that our aircraft wing is capable of both torsional twist and bending, and we'll see that sweep introduces a coupling between those two. So it increases the coupling between elastic bending and torsion. So let's remember what these two things are. So if I have my aircraft, drawn a terrible aircraft here, but let's say I've got an aircraft, I've just drawn the longitudinal axis. If I was to draw my undeflected wing here, then bending, the aerodynamic load is going to have a tendency to cause the wing to bend upwards. Let's draw that in red because it keeps it consistent. So the aerodynamic load and as we've already shown from torsion, we see this increased delta theta. Okay. So bending, let's just draw a little bit more about aircraft bending. So if I was to look at the wing front on our aircraft, so my x-axis is going towards me, I've got my minus y-axis and my z-axis. If I've got my undeflected aircraft wing in yellow, I could overlay my deflected wing. We could describe bending as this negative W displacement, we'll say. Okay, so this is my bending. W, that's just the symbol we give for this displacement. We have U, V, and W associated with X, Y, and Z. Because we're going to use this nomenclature because it keeps us consistent with other courses and with textbooks for this course. So let's see if we can work out a model that couples this bending and torsion due to twist. Sorry, due to sweep. So if I have my unswept wing, then I've got basis vectors which I can write as I and J. And I'm going to overlay a swept wing, and we're going to put positive sweep here. Let's make that wing slightly smaller. I prime and J prime. And so this angle that we've got is lambda, which is my sweep angle. So let's write this down. So I and J are the basis vectors on an unswept wing and also on the aircraft body. So the free stream on both the unswept wing and the swept wing, the free stream is always going to be along I, okay? Never going to be along I prime. And that's where we need to resolve the angle of attack. So we'll think about that in a moment. I prime and J prime, basis vectors of the swept wing. So the reason that we introduce these basis vectors is because when we're talking about bending and torsion, occur within this coordinate system. Angle of attack occurs within this coordinate system here. Okay, so we want to see if we can work out the relationship that relates these two things together, because we already know that we already have from the previous lecture that the angle of attack is equal to alpha prime plus delta theta. So this is total angle of attack. This would be the rigid angle of attack. And this here would be the elastic change in incidence. So this expression, as I've written it here, is actually only valid for a straight wing. And when we introduce sweep to this problem, then we have to change the mathematics slightly to allow us to accommodate sweep here. So we need to then look for what's the effective rotation around about this J, okay, because that's the angle that we care about, if we have both bending and torsion occurring. Because when we've only got if we have a straight wing, bending doesn't do anything to the change of angle of attack. But when we've got a swept wing, bending changes the angle of attack, and we're going to look at how we can relate those. And so we then need to look at a term that we can replace delta theta with that defines the total rotation around J because of change to bending and change to twist. Excuse me. Hello, Harry Smith speaking. That is correct, yes. They did, but this sounds like you're looking to make money off of stuff that I've done. So I appreciate this, Jess, but no one's going to reach out to me and give me money that I've got. Your company's profiting from it. So I'm going to say goodbye. Okay? Take care. Okay, so for the swept wing, we need to define a change to AOA, which is a rotation around J. Due to both bending and torsion. And thankfully, our old friend, the Euler transform, with which you're going to get very, very familiar next year, will help us. So thankfully, an Euler transform relates these easily. So let's do a quick Euler transform. If I've got my unswept basis vectors I and j, and I've got my swept basis vectors I prime and j prime. It's really important that you get the right signs on these. Okay, so we've got I, j, k must be going into the page. Positive rotation is defined around here. Okay, so I'm going to do a quick Euler transform. I've got I cosine lambda, I sine lambda, j sine lambda, j cosine lambda. I could then write expressions for I prime and j prime in terms of I and j. So I get I prime is equal to I cosine lambda plus j sine lambda. J prime is equal to j cosine lambda minus I sine lambda. K prime is simply equal to k. So then I get this rotation matrix. I prime, j prime, k prime is equal to cos lambda, sine lambda, minus sine lambda, cos lambda, 0, 0, 1, 0, 0, I, j, and k. So I've got this rotation matrix now that enables me to relate quantities in my swept reference frame from my unswept one. And then I could write this as I prime is equal to this transformation matrix multiplied by I. And then I could see that actually I'd want the inverse of this matrix to go the other way around, but because this matrix is symmetric, that's just the, sorry, the matrix is not symmetric, but because it's orthogonal, the inverse is simply the transpose of this matrix. So I could similarly just write this. This is very easy to copy. Just get rid of all the primes from this side. Swap them over to here. And I just need to change the sign of my sines. And that gives me two relationships that I will need. So here I've got my rigid, or my unswept reference system. So that's the body axis reference frame as a function of anything in the swept reference frame. So it's actually this one here that I want. So let's go back to the problem here. We said that we needed some effective change to angle of attack because of both bending and torsion. So that's going to be a rotation around the j axis. If I put my thumb along here and curl it round, a rotation about the j axis, I'm going to have an increase or a decrease in effective aerodynamic incidence due to a combination of bending and torsion. So I need to use this middle set of equations here. So we need to look at the J equation. J is equal to I prime sine lambda plus J prime cosine lambda. So we could say J is going to be our elastic change to angle of attack. So we'll call this delta alpha elastic. Going to be equal to I prime, so I need to look for a rotation around I or I prime. A rotation around I prime, this is my vector around here, so rotation around I prime is going to be due to bending. So let's just go back up here, where I've drawn it. I've drawn my bending somewhere. Okay, so if I've got a wing that bends down, that gives me positive I prime, but because I've got a wing that goes upwards, that gives me a negative I prime in this sense, because bending is defined positive up. So we get delta alpha, this I prime, if we're looking at rotation around I prime, it's going to be minus dw on dj, so the slope of whatever the bending oscillation, so the slope of whatever the bending displacement is going to be, multiplied by sine lambda plus, and then I've simply got to put in the change to deflection. So the J rotation, remembering J or the J prime rotation, that's the rotation around J, that's simply whatever the torsional twist was on this wing. So this equation here tells us that elastic change to AOA is equal to rate of change of bending and that's again just with respect to the span-wise axis, and then this last term here is torsional twist. Let's just erase that, so that's actually a lambda and not an A. Now this expression here we can use in place of the delta theta here. So I'm going to rewrite this expression now for a swept wing. So we have total angle of attack. It's equal to the rigid AOA plus any torsional twist minus any bending, as long as lambda is bigger than 0. If lambda is equal to 0, then we just get rid of all of these terms here and we've got the same expression as we had before. Okay? If lambda is positive, so this expression now means that any torsion is going to be reduced, but importantly, if the wing bends up at all, it reduces the angle of attack, as long as lambda is bigger than 0. So if lambda is bigger than 0, which is aft sweep, bending reduces the angle of attack. Okay, and in both cases, let's go back a second. If lambda is bigger than 0, if we have aft sweep, bending reduces the angle of attack. If lambda is less than 0, forward sweep, then bending increases the angle of attack. So that won't be good for us. We want this idea that any wing bending, because we're always going to have bending under lift, we want it to reduce the angle of attack. So what we've just shown here is that aft sweep introduces a negative coupling between wing bending and the angle of attack. So because the wing bending is also going to be a function of the lift produced, any increase in bending, as long as we've got aft sweep, reduces the angle of attack, which serves as some negative feedback within that same loop that we had for torsional divergence. So we can't easily include this in this whole problem here, because at the moment we're assuming that delta theta is only a function, well, this is just the torsional twist. We can see that actually, when we were to account for this in the angle of attack, then we'd see that actually that torsional twist would be reduced by the cosine of the sweep angle and also reduced by any bending as long as we've got aft sweep. Conversely, forward sweep introduces a positive coupling, means that if we bend upwards we have this increase in angle of attack. So this is why we have aft sweep on most aircraft. Okay, it's to reduce the to increase the divergence speed. Now, if you are having trouble visualizing this effect, then get a ruler, get something flexible, get a scrap of paper. And let's imagine now that this is my aircraft wing, or one aircraft wing. Now I'm gonna say this is my aircraft, because I can't easily sweep this aircraft or bend it. Let's say I've got this wing. Okay, so my fuselage is on this side, tip is on this side. So let's just get rid of the aircraft, and let's imagine the case where I've got a straight wing. Now, an increase in torsional twist causes the underside of the wing to be presented to the flow. That gives us an increase in angle of attack. Now, if I have large wing aft sweep, then an increase in bending presents the upper side of the wing to the flow, which is a reduction in angle of attack. If I've got an unswept wing, bending doesn't change the angle of attack at all. If we have forward sweep, then an increase in bending presents the lower surface to the flow, i.e. it increases the angle of attack. So let's just go through that again. Straight wing, that's my fuselage. Okay, remember that presenting the underside of the wing is an increase in angle of attack. Any bending for an unswept wing doesn't do anything with the angle of attack. If I've got aft sweep, bend upwards presents the upper surface to the flow, which causes a reduction in angle of attack. And if I've got forward sweep, a bend upwards presents the lower surface of the flow, which is an increase in angle of attack. So grab a piece of paper, play around with that, and that will hopefully help you understand why aircraft predominantly have aft sweep. There is this reduction in critical Mach number, and that can help us for aircraft that do fly transonically or at high Mach number, but predominantly aft sweep is there to increase the divergence speed because of this negative coupling that it introduces between wing bending and the change to angle of attack because of deformation. Cool, so we've done that, we've gone through it. I'm going to go through one more topic next week, which is control reversal, and then we're going to look at some questions that you will be expected to be able to answer for this course. I hope it's been enjoyable. I love this topic. I love talking about divergence, and I love talking about control reversal. I really love talking about flutter, and I might produce some extra lectures on those anyway that you guys won't watch, but I'll provide them anyway. Okay, hope you guys are having a wonderful week, and I look forward to seeing you guys in the review, which I think is going to be on Thursday now. Take care.